In the world of real-time and embedded systems, everything feels like it's happening all at once. You've got multiple threads running, you've got interrupt routines firing off, and a lot of the time, they all need to touch the very same piece of data. Now, that sounds simple enough, right? But it's actually a minefield for these really subtle, nasty bugs that can totally corrupt your data and bring your whole system crashing down. So how do we deal with this? Well, let's dive in and look at one of the most elegant solutions in the Zephyr RTOS, atomic services.
And this question, it really cuts right to the chase, doesn't it? This isn't just some academic thought experiment. It's a super practical problem that every single embedded developer runs into. When two or even more different contexts, like your threads or your interrupts, are all racing to get to the same shared data, the result is completely unpredictable and almost always wrong. This whole scenario has a name, and it's kind of the villain of our story today, the race condition. So let's step right into this danger zone and see what a race condition actually looks like in the wild. Picture this. You've got thread A and thread B. In front of them is a whiteboard with the number 5 written on it. Their job is dead simple. All they have to do is add 1 to that number. Now, if they do it one at a time, no problem. But in a real-time system, they're often trying to do it at pretty much the exact same time, and that is where all the trouble begins. And here's how it all falls apart, step by step. So, Step 1, thread A reads the value, it sees 5. But before it gets a chance to write its new answer, the system switches contexts. Then, step 2 happens. Thread B also reads the value, and it also sees 5. Now, in steps 3 and 4, they both do their math correctly. They both figure out that 5 plus 1 is 6. But the absolute critical failure is in step 5. They both write 6 back to the whiteboard. So we've done 2 increments, but our final value is 6 instead of the 7 it should be. And boom, our data is officially corrupt. Okay, so how do we fix this mess? How do we make sure our simple little counter actually, counts? This is where our hero shows up, atomic operations. The word atomic, it actually comes from the Greek word atomos, which means uncuttable or indivisible. And that is exactly what these operations are. They are single, uninterruptible actions that save our data from this kind of corruption. Let's get the official definition, straight from the Zephyr documentation. An atomic variable is a variable that can be read and modified in an uninterruptible manner. That's the magic phrase right there. It means that the entire sequence, reading the old value, doing the math, and writing the new value back, all happens as one single, indivisible step. No other thread or interrupt can sneak in the middle and mess things up. This quote from the docs really drives the point home. It's not just a suggestion or a good idea, it's a guarantee. Even if some higher priority task swoops in and tries to interrupt, the atomic operation will finish correctly. This is the kind of rock-solid reliability that is absolutely non-negotiable when you're building robust embedded systems. So, we know what atomic operations are and why they are so important. Now, let's actually open up the toolbox and see what functions Zephyr gives us to put all this theory into practice. First things first, you have to actually declare an atomic variable. And it's incredibly easy. You just use the special atomic T type. By default, that's going to be initialized to 0 for you, but if you need a specific starting value, like the hexadecimal FF you see here, you can just use the atomic init macro to set it up exactly how you want, right from the get-go. Let's go back to our counter problem. Instead of a regular integer that can get corrupted, we define it as atomic T call count. Then, whenever we need to increment it from any thread or any interrupt, we just call atomic inc. This one function call wraps up the entire read, modify, write operation into a single, safe, uninterruptible action. It's clean, it's safe, and it just works every single time. And that simple increment function is really just the beginning. The Atomic API is a whole toolkit, and it's organized into these really logical groups. You've got your standard arithmetic operations for things like counters. You've got these powerful bitwise operations, which are absolutely perfect for managing things like status flags. And of course, you've got the basic get and set operations for reading and writing values safely, including the super useful compare and set function. Okay, let's dig into that bitwise category for a second. Because in embedded development, we are constantly fiddling with individual bits, right? We're managing hardware registers or complex state machines. And Zephyr's atomic services give us this incredibly precise control to do all of that safely. So what happens when you need to manage more flags than can fit into a single 32 or 64-bit variable? I mean, a single atomic T isn't going to cut it. That's where this awesome macro, atomic define, comes into play. It lets you create a totally thread-safe array of bits, a bit field of pretty much any size you need. You just give it a name and tell it how many bits you want, and the macro takes care of all the tricky memory layout stuff for you.
And once you've defined that big array of bits, working with it is super easy. The API gives you all the tools you need to reach in and flip a single specific bit. You can safely set a bit, clear a bit, or even just test what its value is, all in a thread-safe and interrupt-safe way, without messing with any of the other bits in your array.
Okay, so we've got this fantastic toolkit at our disposal. But, a truly great developer knows not just how to use a tool, but when to use it. So let's talk a little strategy. When should you reach for an atomic operation instead of, say, another concurrency tool like a mutex?
The crucial thing to remember here is that this isn't a one-size-fits-all deal. Think of it like this. Atomic operations. On the left, they're like a surgeon's scalpel. They are precise, they are lightweight, and they are incredibly fast. Often they boil down to just a single machine instruction. They are the perfect tool for protecting a single variable. Mutexes, on the other hand, they're the heavy machinery. They've got more overhead because they're a full-blown OS feature, but they are absolutely essential when you need to protect bigger, more complex data structures or even entire blocks of code. And hey, don't just take my word for it. The Zephyr documentation says it right here. When your job is just to protect a single value, using atomic variables is far more efficient. This is a huge takeaway for anyone who cares about performance. If an atomic operation fits your use case, it's pretty much always going to be the fastest and the best choice you can make. All right, let's bring it all home. If you only remember one thing from all this, make it this. Atomic operations are your concurrency superpower. They give you the ability to write code that's fast, correct, and reliable, even in the most complicated, multi-threaded environments you can dream up.
So what does that superpower get you? Well, first, that uninterruptible guarantee, which protects your data from corruption. It gives you high efficiency, which means your code runs faster than with those heavier alternatives. It offers incredible versatility, working perfectly in both your normal threads and in high-priority interrupt routines where you often can't even use a mutex. And finally, it gives you that fine-grained control, right down to the individual bit. It is an essential, powerful, and efficient tool for any Zephyr developer.
And that's where we'll leave it. We've seen the very real danger of race conditions, and we've walked through the elegant and powerful solution that Zephyr's atomic services give us. They empower you to write code with confidence, knowing your shared data is safe and sound. So the only question left is the one right here on your screen. Now that your data is safe from corruption, what will you build?